before you. I think you can share your screen.
Sounds good. I was before. Should come up in a second. Okay. See that okay?
Yes.
Okay, awesome. So I think I stopped somewhere in here. I was just going through some sort of basics on basin and range tectonics, mountains forming, valleys forming through normal faulting, and showing some examples of fault geomorphology, types of things we look for when we're trying to map faults. And I believe I showed this slide before, but it's really a beautiful picture of triangular facets along this range front, which is the Cortez Range, which is in central Nevada, just south of Highway 80. But also in the middle of this picture is the Wineglass Canyon. So you want to clue your eyes in on this. It's a really diagnostic feature. And each time there's an earthquake, there's incision through the scarp that's created along the base of the mountains. And that's basically the stem of the Wineglass. And then the opening of the Wineglass towards the sky. So it's a really diagnostic feature, and we see it all over the place. And then I showed this before as well, but just to get back into thinking about normal faults, we talked about the alluvial fans coming out of canyons, like this photo on the lower right. The truck is here for scale, and this is the scarp across an alluvial fan. And so and last time is that we look for where fans may be cut by the fault, and it's only several locations actually, typically along a range front where you see this. So you really have to hunt and look in each stream valley mouth and find places where quaternary sediments have been deposited across the range front. But like I said, they can be few and far between, but once you find them, you got really good evidence of displacement in the quaternary. Basin facing scarps. So typically the scarps face towards the basin. There are grabens where the scarps face towards the mountain sometimes, but most typically normal faults will have scarps that face towards the basin. This is Simpson Park Mountain over here on the left. That's me for scale standing there. So this is about a 4-meter scarp. And then this is about a 6-meter scarp along the Shell Creek Range, just close to the Utah border along Highway 50, about 20 kilometers from the Utah border. Just a really beautiful, this time in, this is the afternoon, this is an east-facing scarp. So this time of day, called the near-tectonic hour, you can see shadows along the scarp. So it's a good time to go out and map because they show up really nicely. We can accentuate that by making hillshades by different angles like we've been doing in class. And you can modify the angle to pick up shadows along the scarp. But in real life, this is what it looks like when you shadow with the late afternoon sun. Here's the Shawabes. Again, there's some triangular facets along the range front. Another feature that's typical is just over steepened range front, so it gets a lot steeper in the lower tens of meters or so along the range front. That's just due to repeated earthquakes refreshing that steep scarp. So in the south part of the range, here's a map of it here. So it bounds the east side of the Shawabe Mountains. In the south part of the range, it extends along the range front, which is this picture up here. But in the north part of the range, there's a step. The mountains become sort of less defined and broader, and the fault is stepped out into the valley a little bit, and that's where these two photos are taken on the bottom here. So there was a trench excavated, the photo in the middle, the trench location is indicated, but what I want you to clue your eyes into is these alluvial units that have streams incised into them and scarps along cutting them. So these are aerial photos taken from an airplane at pretty low altitude. And then the photo on the right is a similar thing where there's a scarp sort of outboard of the bedrock. There's alluvium coming out of the bedrock that's cut by this fault that runs along. So in general, they generally parallel the range for the most part, but step out from the range in some places. So it's something to look for. So here's the Humboldt range, and this is sort of the crux of what I want to get across to you. When you're mapping normal faults, you really look for quaternary deposits of different ages. Whenever there's a displacement event, it tends to preserve a surface on the footwall of the fault. And so in this photo here, this is the Humboldt range. This is heavily dissected surface up here. That would be, we talked about old, intermediate, and young surfaces. So this is a pretty dramatic example of the drainages that are really deeply incised, they're tens of meters deep. Okay. And then when you look to the left, there's another surface here that's a little less developed drainage network. This would be the intermediate age band. And then even there's a young band on the far left edge. And so the fault runs right along the front of this preserved old surface. You follow my cursor. And then it cuts across the front of this intermediate surface, and then actually cuts across the young surface. And you can't really see the scarp in the young surface because it's really small. But you can see this sort of change in tone and color across the intermediate surface. That's where the fault's running there. And then across the front of the O surface. So it's a really key relationship of three different ages. Okay. And so that's what we really want to look for. So in this case, there's two events in the last 4,600 years or so. But there's also shorelines that come up from Lake Lahontan, so you can confuse those with fault scarps as well. So let's be careful on which geomorphic landforms we're looking for. But when you see this progression of different age surfaces with progressively smaller scarps on progressively younger surfaces, you're in the right location to be mapping the fault. So yeah, it's tough to read all these, but we talked about GIR indicators, strike slip faults. We've already gone through that. Normal faults, there's some of these terminology I've been going over: triangular facets, graben, scarps, oversteepened range fronts, wineglass canyons, beveled scarps where the scarp may change slope down the face of a scarp, so that indicates multiple events, and distributed fracturing. So those are some of the terminology that I've used in the past mapping. We've sort of defined it with a little bit more detail with the GIR for this class. Other things we note is vertical separation or scarp height. As we walk along, that's more of a field thing. You know, we can generate scarps in QGIS too. So look at scarp heights, which we're working on for your homework this week. And so I just put up these. I'm not going to read through them all. You have them in your handout from class. But you know, we've given the rankings, so similar to the GIR for the other types of faults. There's various things that are unique to normal faults, like Sackum, distributed fracturing on ridge tops, and graben, sort of depressions along the range front, fissuring, oversteep and range fronts. But all those terminology that I mentioned in the last slide are kind of worked into this GIR table for normal faults. And I want to emphasize that these aren't all of them. You might see some term or some descriptor that may be unique somewhere, and you can make up your own. I see a question, hand up. Mara, do you want to go ahead?
Yeah, a question about like when we're looking at all of these features, how do we use the GIR to map geomorphology that's not around the fault? Because these are all about the faults.
These are all about the faults, you're correct. So these terms you'd be putting sort of along the faults, right? So if you're mapping geomorphology, you'd use different terms. So these terms that I'm showing right here on this slide are specific to along the fault, pretty much. So, but you could use displaced landform or something like that, which was included in some of the other fault type. But so I think what you're saying is there's geomorphology elsewhere, broader from the fault, and how you would capture that. Chelsea, do you have any ideas on that? Chelsea, you're muted.
No, actually, could you say that question again? Sorry.
Well, just mapping geomorphology outside, distant, far away from the fault using the GIR. So if we're using GIR for normal faults, but you know, how would we capture different geomorphic observations away from the fault?
So in the main assignments that are coming, we do give you a polygon to map, and it's not that far from the fault. And so we're not actually hiding the location of the fault that well because it's kind of in the middle. So it's important though that in that whole polygon, you do look for the geomorphology that could be indicative of fault, because that may be still where secondary faults are located.
Things like triangular facets too are not necessarily right on the fault, you know. So I mentioned last time that they start with a small triangle near the active scarp, but that they go up and fractally get bigger and bigger going up the range front. So you could map triangular facets, you know, away from the fault on the range front further up the mountain. So that'll help fill it in a little bit.
And to add to that, if you're using the GIR, it's mostly to help you locate the fault or find features indicative of faulting. So if you want to map the geomorphology away from where the proposed fault location may be, you can still refer back to the morphologic mapping style and your general like geomorphology mapping style if you'd like to do that. And if it helps you find the GIR features, you can map out simple drainages or the slope breaks convex concave down too.
Right, so morphological mapping, and then also polygon mapping like we did in the Landers assignment. If you see geomorphic units, if it helps bring your eyes to where the fault might be, you can map those out as well. But not really required for normal fault homework.
There's lots of, well, I was just going to add that there's lots of, I think there's still some generic GIR elements that we have in the one that Rachel has provided, and some of these other ones like springs are, you know, could be anywhere. So I think, you know, it's tried to have a broad coverage of your mapping, but then go ahead and use some of the other generic GIR components to help where, you know, where you see them. And the idea is that you would probably only find these kinds of fault related GIR features near the fault. So it's kind of self-evident in that sense, hopefully.
All right. And use them as how you see fit. So I was going to talk. I don't have a ton of time, but I do have more time next Thursday as well. So I was going to talk about historical surface structures. I'll mention a few things about this, but I definitely want to show you some other mapping that will help you with the homework. But I just wanted to show a few of these. I'll probably talk in a little bit more detail on these next Thursday, this coming Thursday. But just here's the 1915 Pleasant Valley rupture in north central Nevada. Here's the map, and it's here in red. One of the northernmost ruptures of a string of ruptures that's known as the Central Nevada seismic belt. So all magnitude 7 earthquakes, all in historic time. But I just want to focus. This is what some of the geomorphology looks like when we get a fresh rupture. So here's a fault plane, pretty steeply dipping. You know, we think of normal faults being around sort of around 60 degrees in Nevada, but when they get to the surface, they steepen up quite a bit. It's probably like 75, 80 or something. But here's a scarp on the lower right. So nice fresh scarp going across the range front. Okay, and it's not a huge mountain here, but it is along sort of the base of the slope, and it's refreshing and steepening the base of the slope. So over time, this will erode and sort of fill in a little bit colluvial deposition below the scarp field. But today, the scarp is still pretty strong. 100 years later or so. So here's just to show that you can have distributed fracturing up in the mountains. So I want you to think about that when you're doing your homework. The fault's not necessarily always right on the range front, although it typically is. There could be other fractures and other displacements further up the mountainside. So these light-toned lines going horizontally across the image are also scarps. So there's a larger scarp at the base, but smaller scarps up in the drainage. So here's where it's going across sort of a really old dissected surface, pediment of some kind. But what you notice is the dark shadow along the front here, and then the dark shadow going across a younger alluvial surface that is inside into this sort of intermediate. So this is, again, would be like an older surface, a relatively intermediate surface, and then a young surface. And they're all cut by this stuff. This is to show like an aerial image. You know, if you're just looking straight down in Google Earth or something like that. The area I was showing before is kind of right here at the bottom of the picture. But it's a pretty nice edge to the mountain front there. And so that's an uninterpreted in the middle and an interpreted fault trace map. So things to think about here when you're working on your homework is, you know, there's steps here where the fault does not necessarily connect. And these are mostly the historic ruptures. This is the last time it ruptured. But it doesn't connect through everywhere, right? So you could have gaps in your mapping. There's places where it gets pretty complex, where there's multiple parallel traces, things like that, like in this central zone. So you'll have something like that in your homework as well. So things to look for. And little steps like this here. Okay, the left step in the system. Okay, so here's another set of historic ruptures. Fairview Peak and Dixie Valley happened in 1954. Those are the light blue ones on this map. There was actually, they actually occurred 4 minutes apart. So it's an incredible release of energy there at that time. And then a couple months later, there was the Rainbow Mountain earthquake to the left, with the blue trace to the left there, which was also a magnitude 7. So 3 magnitude 7s in the course of a couple months, pretty dramatic. And here's some of the scarps. So the middle photo is the scarp of the Fairview Peak. It's about a 2-meter scarp, and it actually had some lateral components to it as well. It was actually almost 1-to-1. So that's something to think about when you're mapping normal faults. You know, in Nevada, they're primarily normal displacement, but we are at a plate boundary, or California is moving to the northwest, right? And there's right lateral deformation in the Walker Lake. And how the fault might be distributed across the landscape. It may not be purely normal everywhere. Here's the Dixie Valley scarp. This is a famous photo where the ranch was back tilted. This shows distributed fracturing out towards this little ranch house. So it's a wide zone of distributed fracturing, actually a little graben along the fault trace, and then about a 2-meter scarp. So there's a geologist standing there, you can barely see in there looking at it. This is just a photo of the Dixie Valley rupture. Distributed channels out here and scarps preserving these older surfaces. And so if you look close, there's a little bright spot reflection in the photo here in the middle. There's a scarp there that's facing towards the basin. There's also a scarp that faces towards the mountain. So there's actually a big graben here that's quite a distance outboard from the rangeland. I can talk about that. Here again, it's the Dixie Valley, but it's an uninterpreted and interpreted map of where the 1954 rupture went. So again, what you can take away from this is that there's a really nice range front trace with sort of sharp faults along those range fronts. But then there's these differences in tones out in the valley where rupture was distributed. And so right here, there's a big right step in the whole system. And so as it was rupturing, it broke the alluvial unit in this step over. Excuse me. Okay, so this is what I wanted to get into. I don't have, how much more time do I have, Kelsey? Like 5-10 minutes or so?
Sure.
Yeah. Okay, and I can go over some more of this, but I wanted to show a few examples of mapping across the Great Basin, these various range fronts. So this Highway 50 goes across the middle of this picture here. And, you know, I've done mapping on a bunch of these range fronts that are labeled here, and I'll show a few examples of that, but the quaternary geology is what I want to highlight, so you can think about that as you're doing the mapping. So we talked about polygon mapping in the Landers assignment and mapping, you know, GIR for normal faults. So here's just a map of the Toyabe range in Big Smoky Valley. And in the next slide, I'll zoom into this central part of the map here. But what to pick out here, there's, first of all, the map on the left shows the fault in white. So pretty sharp range front trace. And at that scale, you can't see things outside of the range front very well. But here's like a final map with intermediate in brown, old age surfaces in orange, and yellow is the young surfaces. Okay, and there's some fault traces here outboard of the range front. So I'll zoom in on that right now, right here. And so this is an aerial photograph, uninterpreted on the left and interpreted on the right. And so the thing to pay attention, I know it keeps saying it over and over again, but it's really diagnostic. It's this old, deeply incised channels in the upper part of the image here. And that's mapped in the green. That's my old surface. And then we use things like cross-cutting relations where this, I called it salt and pepper when I was in the field, but it kind of has that look of sort of black and white speckled on the air photo. But along the very top, there's this fan that kind of comes across, it's cutting across this older unit. So I mapped that as intermediate, and basically just using the cross-cutting relations of the two deposits to pick out their differences. And then in the middle part of the photo here, there's another QFI surface, and it's incised a little bit, but these drainages are only incised like less than 4 meters or so, whereas these are incised tens of meters, several, maybe 20 meters or so. So it's a marked difference in the drainage geomorphology, okay? And then there's some basin-facing scarps that show up nicely across the old surface is preserved on the footwall of the scarp. And then the scarps get smaller, you can see these real light-toned lineaments that are cutting obliquely across the drainage direction. And then the yellow is the young, which projects up some of these drainages here. So you use the air photo and your eyes to really pick out these different units. And the scarps kind of map themselves in a sense. Once you have this like old surface map, you kind of know at least where what part of the scarp is. And then there's details like a little shadow here, difficult to pick out sometimes, even sometimes really hard to find in the field. There's some distributed faulting down in here as well, but that's a little bit more difficult to pick out than the main traces. So this is another instance where we see a young fan, and I didn't really map this. On the photo, I didn't map the boundaries of the units, but I did in this little blow up here. There's this road is in black, the road is in white on the photo. So this is just an instance where the young fan doesn't have a scarp on it at all. There's a 2-meter scarp across an intermediate surface. And as you go to the north, you get progressively more and more development of the drainage network. The scarp's about 2 meters in QFI. It's about 10 meters in QFO, and it's about 30 meters on this sort of pediment surface where it's starting to separate bedrock from the deposits in the basin. So it's just another example where we have progressive deformation, and we use sort of the different age surfaces to help clue our eyes into where the fault is located. And I can stop anytime. I just want to leave enough time for Ramon. We can go over these some more examples of these Thursday. But it goes on and on. I have many of them.
I think, yeah, this is probably a good place to stop. And then Thursday also, we can bring in some of the questions from the reading from the students.
Okay, yeah, that'd be good. And we'll eventually go over the homework, the normal fault homework after we graded it. But the point is you guys to just look for GIRs and not really have the answer, right? So these are just examples to help your thinking on how you would zone in on where the fault might be.
It's due on Tuesday next week, and I think we'll go over it
Yeah.
on Tuesday. So it's instant
Okay,
feedback
yeah.
before we grade it.
Yep. So let me stop sharing and I'll turn it over to Ramon. Thanks, guys.
Okay, any quick questions for Rich? As Rich said, there'll be some more time, but let me just dive in here, guys, and let me make sure I've got everything ready. Okay. So the point of this lecture is just kind of some review, a little bit of some kind of strategic commentary about mapping to sort of help launch us. As Chelsea said, we're going to move into you guys mapping separately, but there's a few more things we might talk about that provide the background and some more examples. So what I'll talk about now is the following, something like this. So I'll review an example of California Geological Survey fault evaluation report results. Kind of how is this done practically by the CGS as one of the world leaders in these topics, because they're sitting on a lot of active faults. Then a reminder of the main motivations of our class, kind of a little bit of some of the philosophical and fundamental components of this activity. And then I'll go back and forth between some of this heuristics by demonstration. So that's kind of like building intuition from examples, which is a lot of what Rich was also just doing. And then I'll dip into something about workflows and database schemas as things to help you think. And so the idea, we want to balance where we're trying to give you some specific tools and specific ways of doing the work, but also to show you that this is consistent with professional practice around the world, and also to just maybe some ideas, some of these examples will trigger some things for you. Did I see a chat? No, we're good. Okay, so let's dive in here. So this is the first example here is from the California Geological Survey fault evaluation report. This is a product that is produced by CGS as a general item that's for planning, and is in response to what they have as the Alcoas-Priolo Act, which is their legal responsibility to delineate fault traces that came from after the San Fernando earthquake in the early 1970s. And so a lot of work over this whole time to produce this information. And so this was produced by Jerry Tryman, who's a longtime CGS employee. And this came to us from Tim Dawson. So the lower right, this is kind of a little piece from his email. He says, plate 2 is useful for the class, a tectonic geomorph map that Jerry produced mostly from older air photos. Also, although the topo base shows many of the features well, I think plate 3 helps illustrate the evolution of many pieces of the data into a unified fault map. So if we start here, this is this part of would be, if you guys know, the LA basin. This is kind of the west side of actually the San Gabriel Valley, northeast of Los Angeles, and there's a fault called the Raymond Fault. And so what was done first was this is, you know, not exactly the application of the GIR, but is, you know, basically a kind of a work through, and you can see these orange features are lineaments, so mostly scarps, and faceted spurs or ridges, which is a kind of like a triangular facet, so it's a broken or sharp scarp. And then he also mapped out erosional features, these on the right, this blue item, and then compiled some other geomorphic features from Buwalda. And you know, so this is kind of a data compilation, mostly remote, so just exactly as you guys are doing. And so in this area, you see this kind of coincidence of many of these lineaments, and the facing direction is basically what the little teeth indicate. And some also GIR sort of delineation and coding. You see, you know, tree line, linear slope, pressure ridge. And so then this is the basis then for the subsequent interpretation. And then we go into this is kind of just a little bit of a zoom here, just to show a little bit of that nice detail. And then we go to a little bit more, and then their kind of interpretation. So from this mapping, then comes the fault interpretation. So you know, so I think that's what we want to keep reminding ourselves, is the you know, this progression from observation to interpretation. And then this would be the final product, which in this case is this Alquist-Priolo Act fault zone boundary. So this is where they've basically said this is where the fault is, and this is the setback zone, so where there would be concern about possible fault rupture.
Can you go back, Ramon, to the last slide?
Yep.
So here, the colors that they're using, I believe, is identical to what we're using for the different fault rankings.
Yeah.
Probably where we got ours from, to be fair.
Yes.
But I just wanted to emphasize that also at this scale, you can see their scale bar of 1 kilometer there. They've done a number of sort of averaging of signals here. And this is probably at a scale that's fairly similar to what you would be aiming for.
Right. And what's important to appreciate is this is 3 different sets of maps. So it's showing Buwalda, who would be the classic geologist, 1940 out there, pre-urbanization. So it's probably possible to see a lot. And then Crooked-All with the red lines, and then Weaver and Dolan orange lines. So you see that, like all mapping, there's some mapping it's pretty easy to replicate. And there's some mapping that the geologists will have different opinions on, and different appreciations for the significance of those features. So so again, you know, starting with these basic building blocks and then working toward a product like this is what we're doing. And this is one application, let's say, for the agency. So I'm going to push on. So then just a little bit of just a reminder, you know, so we're trying to do this work so we can answer the question ultimately of what's the fault rupture hazard at sites near active faults. Like you know, our example is the, you know, fault crossing pipeline, but many features could be subject to some hazard from ground rupture. And so the first step is what we're doing in our class is mapping the fault traces and deformation zones relative to that were active in the recent geologic past. And so we're trying to give you this toolbox, which includes morphologic mapping, superficial geologic mapping, the geomorphic indicator ranking, and then other things you might have in your toolbox are the fundamental structural geology and geomorphology that we have been touching on in these lectures, your awareness of quaternary climate drivers, the tool, QGIS, etc. So this is one thing that was kind of an inspiring a quote from Steve Thompson, who we heard from recently, and I mentioned this before when he spoke to us, but I think it's extremely important, and it's something we take as a challenge, which is, he says from the standpoint of improving PFDHA models for hazard, it will be most helpful to have the pre-rupture maps reflect the current standard of practice for mapping fault location, location uncertainty, etc. This standard of practice does pay attention to reasonable geologic constraints and follows well-traveled heuristics or rules of thumb about which features are good proxies for active faulting versus differential erosion and not active faulting. So this is something I want to just kind of keep remembering. Kind of what we're trying to do is get you guys up to that ability to produce this current standard of practice. And the comparison of pre and post rupture mapping should be the objective test for us all to learn how well the fault mapping following current best practices serves as a predictive tool for future surface fault rupture. We want to use this comparison to develop additional data for calibration of the PFDHA models, as well as assess the best approaches for producing useful map data. So especially this latter statement, that assessing the best approaches for producing useful map data is what we're trying to do with Rachel's work, and why we're teaching this class again is, and kind of have some of these sort of formal issues we're trying to work through, is how do we do this? How do we bring you guys up to speed? So the challenge then is for us to balance moving our mapping closer to those standard of practice without also introducing too much additional bias or too much reliance on prior knowledge. But it has to be in there some. And this is a standard, this is a generic challenge for many situations. And so with you guys as the motivated students, we can work toward it. And what I think what I'm trying to say with the prior knowledge is that many experts have basically seen every example of surface rupture that has happened in the historically. And so they're not suitable for a lot of this experimentation where we do pre-rupture mapping, because you can't unsee a rupture. And so this is why you guys are, I like to say, you're pure. You know how to do these things, but you're not, you don't have that prior knowledge that basically diminishes the power of our work. And that's why also, as we move towards to the assignments of the mapping for the students, you just cannot let yourself look at examples of these ruptures, because it just kind of defeats the whole point of what we're trying to do. So did I see another chat? No, okay. So just a few more kind of summary points here: mapping strategies, guidance, and considerations. So we're doing this work with these standards. We followed an example from CGS. I'll show this McAlpin flowchart in a moment. We're aware of, controls by fault slip rate, fault type, vegetation, anthropogenic effects, active and paleo surface processes, and we'll see some more examples. That's the heuristics by demonstration. So as we think about our maps, the basic rules as we rate them are, are we getting the position of the bedrock and quaternary geology correct based on what's evident from the imagery? Do we have even coverage, and are we consistently mapping? If you map one thing somewhere, you should kind of map that same way across the area. And really want to have in your mind this idea of documenting your decision making. Is the feature related to active faulting? Do the faults that you've mapped are they supported by the observations? And so that's why maybe it seems to kind of really belaboring the point, but I really think that using these tools to produce observations that then lead to the fault interpretation is the best approach mentally for the work. So one question that comes up sometimes is well, so what's an active fault? And what does active mean? And so usually it's defined by recency of last ground deformation. So I show on the right kind of the last 1.5 million years, just to remind you of the geologic time scale. The Holocene starts 11,700 years ago. And so the USGSQ faults have 5 classes: historic, Holocene to latest Pleistocene, late Quaternary, mid-late Quaternary, and Quaternary. On the other hand, CGS basically says it's Holocene. If it cuts something that is Holocene age, it's active. On the other hand, California Division of Dams says late Pleistocene. If the faults cut features that are less than 35,000 years, they're active. And we want to just remember why the Holocene matters is that it's really post-latest glacial maximum. So many landforms, many landscapes are kind of reset and reconfigured at the time of the last glacial maximum, even if there weren't glaciers there, just global climate change, changing alluvial fan processes, fluvial processes, and potentially glacial processes, and we know sea level all had a huge sort of punctuation at the LGM and then coming forward into the Holocene. So just as a reminder, this is a kind of in the fine print here, but of course this will be available for you afterwards. But this is the Quaternary. The vertical axis is time going back to 2.7 million years ago. And then across here is all the different things that we know and can measure across the Quaternary. And so kind of how things have changed. And so the most common thing is to look at the marine isotope stages here in this third column. And this is a real kind of the key proxy of fluctuation of global climate, but that maps into many other things, including dust, for example. And then on the far right, you can see an effort to just identify that, you know, there's every country, every place has kind of different nomenclature for some of the main sort of time breaks, what they call the different time breaks, which are associated with kind of key events in the landscape. So that's I just want to pause for a second if there's any questions. That's kind of a, I don't know, I'm just sort of, you know, my professorial pedantic commentary on what hopefully you guys want to be keeping in mind. Anything? Everyone's still paying attention, right? It's not too boring and you started doing something different. Okay, let's move on. Okay, so then the next thing is this heuristics by demonstration. So as just like when we teach many things, we show how it's been done before. And ideas that you kind of get some good ideas or maybe see some things that are examples of places or processes that we haven't otherwise talked about. And so, you know, all of them are right in some ways and probably wrong in other ways, but let's just look together at them and see, you know, how other groups have solved some of the problems we're talking about. And this is not exhaustive, but let's look together for things like the morphologic features, how that's used for GIR, how it might be used, different kinds of GIRs, superficial geologic mapping, how the different groups kind of identify primary versus secondary faults. And again, how well are the mapped features supported by the data? These are mostly good examples, published, peer-reviewed, so they're mostly pretty well supported. But we'll see always there are you know, ways to improve or different perspectives. So the first thing is something from Rich. This is from the Enriquillo Plantain Garden Fault in Jamaica. And it's important, I wanted to provide this because it's kind of a lower slip rate fault in a fairly kind of tropical or humid environment. So vegetation is going to be a big deal. But you can see, and one thing I really appreciate about the work that Rich has done is he always does remind us of these GIRs. And so, you know, it's maybe like we have this kind of, we're trying to do a really formal GIR, we call it that, but always in this work, there's always an effort to identify point features that are indicative of the faulting or what's used to support the interpretation. So let's just step back for a second. So this is published in BSSA in 2013. But if we step back, this is in Eastern Jamaica. And these are just my figures, just quick screen caps from Google Maps, just to show you the vegetation is pretty important, and also the agricultural modification of the landscape. But you can still see some breaks and disruptions. And then as we look here on the lower part, we see kind of this alluvial plain with then some indications. This is, you know, this is not something that someone's going to map in 5 minutes, but a kind of a systematic working through these data using your tools should help you to come up with some idea of where active faults might be. And so here is then an example then of the result. And so I'm just kind of jumping around, but if you guys look at this this little feature right here, it's a little like kind of a bump that's out in the valley. That same feature appears in the next image. It's over here. And then as we zoom in to this area here, we'll see that in the next slide. You see right in this area, and I'll let Rich correct me later, but let me just talk through this since I had sort of prepared it. But you can see there's a fairly good set of kind of truncated drainages along this sort of river. But then there's a kind of a complex zone in this area that they noted that I think was key for their work. And then that feeds into this next drainage, this next river valley on the left. And so let's just look at the map product for this area. And so you can see, remember how I talked about a fairly sharp and narrow valley containing the fault zone. And then this kind of little complexity, both in the geomorphology as well as the fault traces, indicated by kind of the abandonment of some of these surfaces. So you see nice quaternary superficial geologic mapping in this area, you know, sort of weaker evidence and really only kind of geomorphic indicators along there taking us into the next piece of the fault. So I think this is a really nice example from a place we haven't looked at, or a landscape type that we haven't looked at as much. And so, Rich, I wanted to just toss it to you to see if you'd like to make a few more remarks. If I missed some things you'd like to highlight.
Sure, yeah, I'd love to. What's really neat about this is, you know, it's where it's really straight and linear on the east side. It's sort of makes this linear valley, but then it starts making a bunch of series of right steps, and it's a left lateral fault. So that's what's starting to generate a lot of uplift, which is, you know, the Blue Mountains are about 9,000 feet, and you start preserving some of the surfaces and things like that to help show us where the fault is. It's tropical, there's trees everywhere, but there's a lot of offset drainages as well. A lot of drainages come down to the fault and flow along it. So that really helps us hone in. But yeah, the GIR was really, really helpful. We had aerial photographs, and then we were checking the aerial photographs in the field and marking those locations. But it's just, you know, you see real nice sort of range front in there with a little linear valley parallel to the range front in the middle of this image, which is, you know, really diagnostic. Faults running right down the middle of that little oval that Ramon just drew. But, you know, it's really just putting the observations of the GIR together all along strike there. We were able to map the fault out fairly well.
Yeah, Aaron has a question. Is there any way on the range front that you would not classify as over steepened?
I mean, it gets pretty steep towards the base. I mean, the whole mountain front is pretty steep, so over steepened is sort of relative in this case. So like in normal faults, like I was talking about earlier, you'll see like a really good break and slope in the lower tens of meters, you know, of the slope. Here it's just a pretty steep, you know, the erosion rates are really fast. It's tropical, it rains all the time, there's a lot of landslides, but it is sort of a steep range right there. And it does sort of indicate a component of uplift. So I think that's related to the right stepping nature as it comes through there.
Yeah, and what I'll just add is this area is kind of tricky because just like, you know, a lot of things where nature likes to make things difficult for us, there's both the fault and the river that are kind of coincident. And so, you know, the fault, let's say, is you know, interpreted to be kind of along here, but also we have the potential for kind of lateral erosion from that river that's going to help sharpen the topography. And so, you know, these multiple processes can maybe produce similar landforms. So we just have to kind of keep our eye on something like that and be patient with yourself with your mapping to say, well, what is all the evidence that I have along here? You know, like this is kind of interesting little kind of a bench or something right there.
Yeah, and I'll emphasize that the stream offsets were really pretty dramatic, but a lot of the other GIRs, like little notches and little benches, were really, really subtle, even in the field, like really hard to stand on, right? So, you know, you can see in this image, there's lots of GIRs like all over the place. A lot of them are really, really subtle, but cumulatively, when you add them all up, they, you know, I mean, you see there's a lot of dashes in that fault trace mapping and stuff like that. But we get a really good indication of where the fault is when we connect the dots of all those subtle features.
Yeah, so this is really, really great. And I'm really excited to show this because I think it hopefully you guys should start to feel like, yeah, I could do that, you know, but again, you know, this takes like if for a professional geologist, you know, you guys went in the field, but this would take, you know, months of work. So at least, you know, putting in tens of hours with the remote interpretation that we're expecting for the class for a project, I'm sure you guys will come up with some good stuff. And, you know, we'll give all
one
the,
more thing on this.
of course.
Yeah, it's just one more thing I noticed that I think is interesting. If you look at the map on the upper right, it's a series of left steps. And then the map on the lower part is a series of right steps. So you get this big basin, this big alluvial basin forming. So in strike slip faults, you can really create a lot of topography when there's bends and steps. And it can be positive topography or negative topography. So, you know, it's transitioning from creating like a pretty sizable basin on the right side of the upper map to a massive mountain range on the left side. And we see that kind of alternating all along. And you think of the San Andreas and the San Gabriel Mountains, you know, and it's sort of the massive scale effect is the mountain building, but, you know, creating stag ponds and stuff is sort of the same thing at a smaller scale when you have steps and bends in the fault and you get pressure ridges or little basins forming. So it's a really good example of like sort of a island scale of that happening here.
Yeah, no, that's great. Thanks a lot, Rich, for that. And I've annotated a little bit. I'm going to push on you guys just to keep going. There's a few other interesting things. So another example, was there a question, Rich?
No, we're just talking here in class of whether there's faults on the south side of the basin. And I was just going to say there's some reverse faults and things like that sometimes display out strike slip faults. But
okay. Okay, cool. So another example, this is a couple things from Northern California. We've seen already some Rich talked about, but I want to show you this Hayward Fault prototype GIR. So this is work done by Jim Leenkamper from the 1992. This is a U.S. Geological Miscellaneous Field Studies map. And they were mapping the Hayward Fault, which bounds the eastern part of the San Francisco Bay Area. And also this William Lettuce and Associates, which is kind of the predecessor of the group for whom Steve Thompson works. But what they would do is they had identified these geomorphic features ranked by a scale of clarity using the following codes. G1 indicates strongly pronounced features, G2 is distinct, G3 is features with weaker expression. And the geomorphic codes don't really indicate that the age, but just sort of activity. And so I won't read all of this, but one of the things that they did, which was kind of interesting, was to do something like what we want to try to do is basically compare a few different parameters along the fault. And so the horizontal axis is distance, and then there's 3 different charts. And so the first one is elevation. So, you know, just where does the fault trace go in elevation? The second one is rainfall. And then the third one is the number of geomorphic features. So this is kind of again a kind of a first order way to look at a GIR. And, you know, what we're looking for, especially the dark, is the high quality, the G1s. And so, you know, where's the most quality of G1 features, as in, let's say, a little bit drier areas, maybe on the ends, and also lower elevation, I guess I should say more, you know, so we see this big area here, these sort of larger proportion of quality indicators in again, a lower elevation. Then it looks like when we go to higher elevations, for whatever reason, maybe you know, the vigor of the surface processes, we kind of lose some of those quality indicators. And then we get to the far end here in the Northwest, and again, we pick up a few more higher quality. So there's lots that we can do when we have this really nice standard approach for collecting these data. And this is just a, simple example, but there's tons to do. And that's why we want to kind of work with you guys. You can see here, they're binning these at 5 kilometers, but that's because they had a lot more time, maybe, and that was kind of the study question. But you can see that bin size, which we've talked about being a little bit more at 1 kilometer, is something that could be varied.
They're also mapping the longer along strike than we will, so it's
Right,
a
70
question of
kilometers.
scale.
So
Ove
Mindy,
has a
this is,
question in a second.
yeah. Hold on just a second. So Mindy asks, where is this on the map? So Mindy, this is basically the whole 70 kilometers of this piece of the, I think maybe, well, hold on, I'm mixing things. It looks like this would be the main Hayward. This is not the diagram on the right actually doesn't go with this. The profiles I'm showing are on the main Hayward up in here. And this diagram on the right is kind of just showing related research. I'm sorry for maybe a little bit of confusion. So other question, did Chelsea, did you say you had a question?
Ove has a question.
Oh, okay,
Yeah,
go ahead.
so the elevation is taken along strike, but I was wondering where the elevation was taken. So is it on the scarp or like on the triangular facets, like next to the scarp, or like?
Probably not too fancy. They probably just used whatever map trace they had as a linear feature that then they queried the DEM. So maybe they did something a little fancier where they did like an extraction on a certain buffer and then did an average elevation along strike. But it would just be, I don't think it was super fancy. It's just basically cutting the DEM right on that trace.
Okay, good, thanks.
Other questions? Okay, let's keep pushing. I'm just looking at the time. We still have a little bit of time, guys. So I'm gonna, Ob, if you're done, put your hand down just so we can make sure when you have the next question. Let's look at some more. Okay, so here's just another example, again, of a product, but also sort of how it's presented. And so this was a final technical report from William Lettis and Associates. They were supported by US Geological Survey to do this mapping. So this is somebody has a job doing this kind of work, which is actually super awesome. And you can see how they did the plotting. And just, I'm showing on the left the kind of coloring. And I think this is also, Chelsea, where we took the coloring for our line work from red to orange to blue. And again, and then 3 classes of certain, approximate, and concealed. And then you can see how it's presented. So this is the final product that comes, after the mapping, the sort of intermediate products like the, morphologic, the GIR, and superficial geologic mapping. So this is the final product, but it wasn't done without a lot of careful pondering of those building blocks. But you can see also this Castlewood Country Club has an interesting little splay going, right through it. Mindy says she lives here or grew up in this area. So did it have en echelon cracks in the backyard? This is the Northern California, but it does have a little bit of creep, right?
Yep.
Yeah, so this is just an example of a product, but just to give you guys a sense of how things look in the end. This one we've seen, so I won't say too much, but I just really appreciate it and kind of shows how we get to our GIR from this earlier work. This is from Rich. Here's another example of Calaveras. This was something that was prepared by Chris Madugo, so I wanted to be sure to share it. And so he's trying to talk here where the consistency of features observed along strike at different scales still have good examples of uncertainty, like where exactly is the fault. And so here's just an image. And then here, so sorry, this is a remotely sensed image of visible imagery. And then here would be a hill shade. And so it's a little bit hard, again, you guys want to start thinking like, where do you start? And so we just start with our GIR and our morphologic mapping, and we see that here, you know, there's a saddle right here that's a little bit unusual. There's maybe a closed depression. There's a couple of channels that may be offset. There's another little small shutter ridge, a couple more shutter ridges. So that's just a quick call. There's a landslide here, which don't be distracted by it, even though it's quite beautiful. The young landslide, there's another young landslide here. And if we go back just to the sorry, I have to. So we see here the kind of comparison of the two data sets, and you want to really be toggling back and forth as you work. And so then here was the final effort or the result with, because there was an area that was trenched, and a comparison of a few different resulting traces. And so you can see there's some variability, you know, between the red and the green and the brown lines. They're all contained within the pink, which would be the Alquist Priolo mapping. But, you know, some debate, you can see there was, you know, difference of opinion here. The green dashed people, they kind of had two traces bounding that pond, a sag pond, whereas other geologists, maybe mapping at a little bit of a smaller scale, had just a single trace, the red line, going on the upper side of that sag. So we want to be, you know, sort of consistent no matter what with how we map, but be thinking, you know, that much more carefully, because, you know, when it comes down to the GIR, to the fault traces, ultimately we really want to know, you know, exactly where is the fault. You know, is it in the middle of that sag? Is it on, you know, one side or the other, or a combination of them? So let me just keep pressing on. Sorry, you guys, when I switch to annotate, then it doesn't let me advance so easily. So it's always a little awkward. Clear drawings. So here's just another comparison of some of the kind of resulting line work that I think Chris Madugo provided. And you want to just see, okay, what's supporting that? So remember, I had identified some of those little shutter ridges, and then I had kind of, in my initial look, sort of maybe missed this little sag there as potentially being meaningful, and maybe some sharper scarps on the side there. So let's push on here. Okay, so is this strike slip? Yes. So this is the Calaveras fault, strike slip fault. So with the strike slip faults, what we often, you know, it's a little bit of prior knowledge, but what we bring to a strike slip fault mapping is usually pretty straight traces, because the fault dip is usually steep, and sort of splaying traces. And then some of these examples we've been talking about, offset channels, sags, so forth. Any comments or questions on this one? I have a couple more I want to get through. Let me push on then. So this is the Alton Tog fault in China. This is actually kind of old satellite imagery. We did this before we had Google Earth access. Really interesting geomorphology and the resulting mapping. So you can see we relied on the superficial geologic mapping here to help us sort of focus in on this pretty complex shear zone here, where this is a left lateral strike slip fault. And this area right in the middle, in the upper part, the figure 8C 905-1, here's a view of that. So you can see a really pretty sag in this landscape, this desert landscape, with these little shutter ridges, kind of en echelon shutter ridges. And then here was a kind of a maybe a somewhat ugly topo map, but made without LiDAR, manual survey with a total station. And this kind of bench right here where the sag is in the middle here. And that was where we could see these main traces, which are quite discontinuous at this scale, but then a kind of a nice little right step. And then we were trying to identify just this local superficial geologic units that could help guide us. And so I want to talk then about some flowcharts that might be helpful for you guys. So this is something from the McAlpin textbook that you may have seen. So he points out, this kind of flow chart of identifying the, doing your regional, doing the photogeologic or image-based mapping as you guys are, with emphasis on the geomorphology and quaternary, and then kind of by homing in on young scarps and then trying to interpret those as being either, anthropogenic, non-tectonic, or tectonic. And then the lower part of this is then to do a site study, but we're really just worrying about the upper part for the fault trace mapping. Here's something that comes from California Geological Survey. Some of their thoughts about scientific confidence. And so if you're pretty confident, you want to say, I am certain that this feature is a fault, versus I can see some kind of feature, but I can't be certain that it's a fault, versus I can't see it at all. And so we want to try to capture this. We don't want to throw away information. We don't want to throw away ideas, but we want to try to code them both in terms of the semantic confidence, what is it, as well as the location confidence, where is it? And so, that scientific or semantic confidence, what is the feature? How confident are we as to what it is? And then where is it? So this is kind of a nice explicit statement about some of these issues. And then this is their workflow, identify all features potentially related to active faulting using LiDAR, aerial imagery, and topographic maps. This is what you guys are doing. The bulk of the work is in that upper one. And then we make this kind of interpretation, assigning the origin and characterizing potential fault features, or saying that they're not faulted. And then here's another one that's kind of working again on a flowchart for confidence. And you see at the bottom right, they always try to have this geomorphic mapping provided for some of their products as a support for the interpretation. And one of the things they say, which I think is really important, and you may have heard me say this a few times, is the word ensemble. So any one feature could be pretty ambiguous, but taken together, this ensemble of features can be important. And so they say, or can indicate active faulting. So as they say, context is important. A single feature, as for example, a spring, may have a low confidence rating that it's fault related. However, put into the context with other features on trend vegetation lineaments, for example, and scarps, the same feature may end up indicating, sort of higher confidence. And so this is what we're trying to take apart with our GIR, is giving you guys some structure to work with this. And then here's just some more. I'm not going to go through this too much, but you can see if you get into this business seriously, there will be, lots of information that's recorded in the geodatabases that back up the line work that you provide. Various kinds of confidence, lots of metadata at the end, and who did it. So we're talking about lines, points, and polygons. You guys are already pretty familiar with this. And then also different, this is again CGS, so they use ArcGIS, and they have kind of preset features for their mapping. And that's kind of what we have now set up for you in QGIS. And so here is another example of their sort of geomorphic mapping on the left, where they have a lot of basically lines and points, and the points would be their version of the GIR. And then on the right is the interpretation, the product, which includes the overall swath of the fault zone, as well as indications of confidence of the fault traces. So I'm just gonna, I think I just have a couple more minutes. Let me check the time here, guys. Oh, I just have 2 minutes. Let me look. What's that?
2 minutes.
2 minutes. Let me just see if there's anything.
Or we can go over it at a different class later as well.
Yeah. Maybe I'll put these up for you guys to look at, and I'll finish on this one. This is just really beautiful, and there's some more details in here, but these are, the Japanese are really experts of this kind of mapping. And so this is a strip map of the median tectonic line active fault system in Shikoku, 1 to 25,000 Geological Survey of Japan map. And I just happened to have it in my office. I took a quick picture of the map, the paper copy, but you get a sense of how it's presented in these strips, and what's being provided is some indication of the superficial geology and coding of their geomorphic indicators. But I'll stop there, and we'll make this available. But hopefully some of these things, you guys are getting more comfortable looking at these kinds of maps, and that it's getting you fired up to make some of them yourself.